Welcome to today's interview training session focused on the vital role of a telecommunications cable splicer. This profession is essential in maintaining the infrastructure that supports voice, data, and video transmission. A cable splicer is responsible for connecting and repairing copper and fiber optic cables, ensuring seamless communication for businesses and residential users. The role demands a deep understanding of cable types, splicing techniques, safety protocols, and technical tools. If you're preparing for an interview in this field, it's crucial to anticipate technical questions, safety practices, and situational problem solving. Let's walk through the top 10 questions designed to help you stand out and succeed in a telecommunications cable splicer interview. 1. What are the key responsibilities of a telecommunications cable splicer and how do you prioritize them on a job site? The responsibilities of a telecommunications cable splicer span several critical tasks that ensure communication networks operate effectively. The role involves splicing and terminating copper and fiber optic cables, reading and interpreting blueprints and schematics, identifying and repairing faults, and ensuring compliance with safety and technical standards. On a job site, these duties require prioritization based on urgency, customer impact, and project deadlines. For instance, if there's a major service outage affecting multiple customers, diagnosing and restoring that service becomes the immediate priority. Routine maintenance and less critical installations may be scheduled afterward. A cable splicer must also collaborate with engineers and line workers, verifying that the proper cabling type and configuration match network design. Safety is paramount, so ensuring the work environment is hazard-free and following lockout-tagout procedures also comes first. Documentation and test verification come after physical work, ensuring compliance and traceability. Prioritization also depends on environmental conditions. Some splicing work may be delayed in harsh weather, requiring adaptive scheduling. Time management, situational assessment, and effective communication are core to managing responsibilities efficiently on a job site. 2. Can you describe the process of splicing a fiber optic cable and the tools you use to ensure accuracy? Splicing a fiber optic cable is a meticulous process requiring precision and cleanliness to ensure minimal signal loss and high-quality transmission. The process starts by preparing the cable, stripping the jacket, removing the buffer tube, and cleaning the fiber strands. Next, fibers are cleaved using a precision cleaver to ensure a flat, smooth surface. The two main methods for splicing are fusion splicing and mechanical splicing. In fusion splicing, an electric arc is used to fuse the ends of two fibers together. This method offers the lowest insertion loss and back reflection, making it ideal for long-haul applications. In mechanical splicing, the fibers are aligned in a sleeve and held together with index-matching gel. This is quicker but may introduce more signal loss. Tools commonly used include a fusion splicer, fiber cleaver, fiber strippers, alcohol wipes, and a microscope for inspecting fiber ends. To ensure accuracy, I clean all tools before use, inspect the cleave quality, and perform an optical time domain reflectometer, OTDR, test post-splicing to confirm signal strength and identify any faults. Proper labeling and documentation conclude the process. 3. How do you interpret telecommunications blueprints and cable schematics to guide your splicing work? Interpreting blueprints and cable schematics is a foundational skill for a telecommunications cable splicer. These documents provide the detailed layout of cable routes, splice points, fiber counts, terminal locations, and network equipment configurations. The first step in reading a blueprint is understanding the legend and symbols used. Each symbol corresponds to specific hardware like splice enclosures, conduits, and cross-connect boxes. Next, I identify the cable paths and distinguish between different types of cables, whether copper or fiber. A cable schematic also outlines color codes and pairing sequences which are crucial for correctly matching wires or fibers during splicing. I pay close attention to specifications like splice tray assignments and signal direction. If working with a multi-fiber cable, schematics help determine the correct fibers to splice together to maintain network continuity. Field changes or red lines are always noted and cross-referenced with project updates. For added accuracy, I verify blueprint data against physical cable tags and location labels on site. Coordination with network engineers ensures alignment between design and actual field conditions. Mastery of blueprint reading allows me to reduce errors, improve efficiency, and ensure reliable connectivity across the 4. What safety protocols do you follow when performing cable splicing in confined spaces or elevated areas? Safety is paramount when splicing cables in confined spaces or elevated environments due to the inherent risks such as electrical hazards, limited ventilation, and falls. For confined spaces like underground vaults or utility holes, I first conduct a thorough hazard assessment. This includes testing for toxic gases, ensuring adequate ventilation, and confirming there's no water ingress. I wear personal protective equipment, PPE, including gloves, goggles, and a harness when needed. The confined space must also be properly permitted and monitored, with a trained attendant stationed outside. When working at heights, such as on poles or aerial platforms, I inspect and secure my fall protection gear, including full-body harnesses, shock-absorbing lanyards, and anchor points. Weather conditions are factored into the decision to work at elevation, as wind or rain can increase risk. I follow lockout-tagout procedures to ensure all electrical sources are de-energized before starting splicing work. Additionally, I participate in safety briefings before each project and ensure that all tools are grounded and secured. Clear communication with my team and having an emergency rescue plan in place are critical parts of maintaining a safe worksite. 5. What are the common faults found in telecommunications cables and how do you diagnose them? Common faults in telecommunications cables include open circuits, short circuits, water ingress, crushed cables, and signal loss due to improper splicing or connector issues. Diagnosing these faults requires a systematic approach and the use of diagnostic tools. The first step is a visual inspection to check for any obvious physical damage to the cable jacket or splice enclosures. Next, I use a time domain reflectometer, TDR, for copper cables or an optical time domain reflectometer, OTDR, for fiber optics to detect anomalies along the cable's length. These tools can pinpoint the location of breaks, bends, or degraded sections. For copper cables, I might also use a multimeter to measure resistance, capacitance, and continuity. Water damage is often diagnosed through a combination of signal tests and visual inspection. Swollen cable jackets or corroded conductors are telltale signs. Faulty splices are identified by high insertion loss or back reflection. Once the fault is isolated, I document it, inform the team, and proceed with the necessary repairs, which might include resplicing, replacing cable sections, or installing new connectors. 6. How do you handle fiber optic cable splicing in extreme weather conditions or remote areas? Working in extreme weather or remote environments introduces several challenges that must be managed with preparation, adaptability, and safety. Before starting a splicing job in such conditions, I conduct a comprehensive risk assessment. In hot climates, I ensure the splicing tent or trailer is ventilated and that tools and fibers are stored properly to avoid heat-related damage. In cold environments, I keep splicing equipment and fiber materials warm and dry, often using heated enclosures or portable shelters. I also plan for longer setup times due to frozen ground or snow cover. In remote areas where access to power or network support may be limited, I rely on battery-operated fusion splicers, backup generators, and portable lighting systems. Communication with the team is maintained using radios or satellite phones if necessary. All tools, spare parts, and documentation are double-checked before deployment to minimize trips back. Emergency supplies and first aid kits are kept on-site. I adapt my workflow and work in shifts to prevent fatigue and exposure. Planning and preparedness are key to executing reliable splices even in the most demanding environments. 7. Describe a time when you encountered a major splicing error. How did you resolve it and prevent recurrence? One of the more memorable challenges I faced involved a multi-fiber backbone cable where an incorrect fiber pairing during splicing disrupted services to a major client. The error occurred due to misreading a color sequence in low light conditions. Once the service team identified the outage, I was called in to troubleshoot. Using OTDR testing, I traced the issue to the splice enclosure I had worked on. Upon opening it, I discovered that two fiber strands were crossed. Blue was spliced to orange instead of its matching pair. I immediately documented the issue, explained it to the supervisor, and began the correction process. The fibers were carefully recleaved and correctly fused using a clean and properly calibrated splicer. I then retested and confirmed service restoration. To prevent such errors in the future, I instituted stricter fiber verification steps, including double-checking color codes using enhanced lighting and a second technician for confirmation before fusing. I also added a checklist process to my workflow, ensuring better accountability and minimizing the chance of mispairing in future jobs. 8. What is your experience with copper cable splicing and how does it differ from fiber splicing? Copper cable splicing and fiber splicing differ significantly in technique, tools, and application. My experience with copper splicing includes traditional methods like twist and cap, insulation displacement, and soldering, especially for voice lines and legacy systems. Copper splicing often involves identifying the correct wire pairs through color codes, stripping insulation, and ensuring a solid physical and electrical connection. Environmental sealing is crucial to protect the joint from corrosion. For larger cables, I use punch-down blocks or splice modules. In contrast, fiber splicing is more delicate, requiring optical alignment rather than electrical continuity. Fusion splicing, cleaving, and microscopic inspection are essential parts of fiber work. The signal in fiber is light, so cleanliness and precision are more critical than in copper, where slight imperfections are more forgiving. While copper cables are more robust and flexible, fiber offers higher bandwidth but is more sensitive to bend radius and physical stress. My familiarity with both allows me to work on hybrid systems and transition clients from copper to fiber where needed. 9. How do you maintain and calibrate your splicing equipment to ensure consistent performance? Maintaining and calibrating splicing equipment is vital for ensuring splice quality and minimizing signal loss. I follow a strict maintenance schedule for all my splicing tools, particularly fusion splicers, cleavers, and fiber microscopes. Daily, I clean the splicer's V-grooves, electrodes, and mirrors using manufacturer-recommended cleaning kits. I also inspect the cleaver blade for wear and rotate or replace it as needed. Weekly, I perform arc calibration on the fusion splicer to ensure proper heating parameters. This adjusts the arc to compensate for environmental factors like altitude or humidity. I store all tools in protective cases to prevent dust and mechanical damage during transport. Before each project, I run test splices and OTDR checks to confirm calibration. Firmware updates are installed regularly to keep devices functioning optimally. When irregular splice results occur, I troubleshoot by reviewing error logs and consulting the manufacturer's guide. Proper labeling, usage logs, and regular inspection routines keep the equipment reliable and field-ready. 10. Why do you think the role of a telecommunications cable splicer is critical in today's network infrastructure? The telecommunications cable splicer plays a pivotal role in today's digital age where connectivity is non-negotiable. With increasing demand for high-speed internet, 5G, and fiber-to-the-home (FTTH) installations, reliable cable infrastructure is more critical than ever. Splicers ensure that data can travel uninterrupted across vast distances by creating precise, secure, and loss-free connections in both copper and fiber networks. They are also first responders in restoring service after outages, making their contribution essential for business continuity and public safety. As networks expand and evolve, the cable splicer supports new technologies by implementing upgrades and ensuring compatibility across old and new systems. They bridge the physical gap in communication systems, making cloud services, streaming, and virtual collaboration possible. Their work behind the scenes is what keeps homes, businesses, and emergency services connected. This comprehensive interview script outlines the core competencies, technical expertise, and practical experiences needed to excel as a telecommunications cable splicer. Mastering these areas ensures success in both interviews and field operations.